Good day, students. Today we're going to talk about light and what it is actually. We're going to talk about the physical aspects of the light and delve into the introduction of the ray optics and solve some problems on that as well, of course. So let's start from our first topic, which is called the nature of light. So basically, have you ever asked yourself what light actually is? And physicists have two answers, which is light is a wave, which is the first answer. And the second answer is called particle. It is a photon. A particle which has no rest mass but still has energy and momentum. Okay, but the thing is, what is interesting about light is that both of those arguments are correct. As you can see it, we call it wave-particle duality because both of the models work pretty well. And in fact, there are very good arguments for both of them and they work for 100% till this day. And also we have the third nature of light, which is called ray. However, ray is a mathematical abstraction, as you can see it right here. So which means that ray is not an actual nature. It's not something like what light is. Instead, it is ability of light to travel in straight lines. So that's a very important thing to note. When we say that light is a ray and we study ray optics, we don't mean that it is a beam of light which consists of something. We just say that it can travel with a straight line and that's it. But the ability to travel in a straight line doesn't make it something new, okay? So let's start from wave, yeah. Okay, what do we mean by light as a wave? In fact, it is not just a regular wave, and in fact, first to talk about wave, let's talk about the definition of the wave. So, in physics, you basically know about oscillations and waves. Yeah, you have studied this way before this course, and as you can see it here, the simple pendulum, and you have some object attached with a rope, and it stands right here, and then it moves back and forth. And again, it continues its movement. In ideal conditions, it keeps its energy, doesn't waste it, but only in perfect conditions, of course, where we have no anything. Of course, we have some gravity involved, and then it just loses its energy due to air resistance and so many other factors. However, let's talk about waves. What are waves? Wave is not the oscillation of a simple thing. Instead, you can imagine it as a water wave. Yeah, it's a very good example. And if we talk about a water wave, in fact, it consists of many different kind of water molecules, yeah, H2O. And the thing is, those molecules individually, they oscillate, okay? However, if we are talking about the entire medium, which is the water, it is not oscillating, it is waving. So what is a wave? Wave is a series, it's continuous number of oscillations which lead to energy transfer without transferring the thing itself. So in fact, when we talk about oscillation of the medium, we're referring to wave. Yeah, this particle of this molecule of the water, maybe it does not go by itself to there, but in fact, this thing can transfer its energy to this place by oscillating other molecules with itself. Okay, I hope that you understood what is a wave, and if you did, I would be really happy. And let's right now talk about the electromagnetic wave. So basically, if light is a wave, it does not tell us about the total nature of light. We can say that it's also just an ability to be a wave. However, what is actually waving? If we know that this thing is not just a regular water wave, it's a wave, but waving, something is waving. In our case, this is just the water. What about this? Okay. If something is waving, what is it? This is electromagnetic wave, which lead to this thing, disturbance in electromagnetic field. You have probably studied this last year, yeah? If we have some positive charge, it creates an electric field out, yeah, like this. And if you have some negative charge, it creates electric field into it, yeah. I hope that you remember it pretty well. But all of these lines of electric field are straight. Those do not have any disturbance. What if I say that those fields might have some disturbance and they might start to oscillate? In that situation, we can say that this thing will become light. But there are several factors which affect it, and let's talk about them right now. First of all, let me take this out and explain to you a little bit further. Okay, disturbance in electromagnetic field. So you definitely know what is electric field, you definitely know what is magnetic field, and when those two fields, or better to say just one field, because further we will see that electric field and magnetic field are not separate things, those two coexist together, but even though, if we consider them as two separate things, it's still okay. Why? Well, let's say you have a magnetic field, which is B, and you have also an electric field, which is just E. And when those start to oscillate together, like this is the oscillation of electric field, yeah, electric field starts to wave. And this is the oscillation of magnetic field. As you can see, magnetic field oscillates by z-axis, yeah, this one. It oscillates up and down, up and down. When we talk about electric field, it oscillates to left and right, left and right, left and right, and so on. Which means that these two don't have to be just vertical, horizontal, they might be any direction, it's okay. But the main thing is to remember that these two things must be perpendicular to each other, which means that those two have to be 90 degrees to each other. That's one of the conditions that I have told you about. And yeah, so what we need for light to exist, we need disturbance in electric and magnetic fields. In those disturbances, those waves have to be 90 degrees related to each other, okay? And also they have to be the same frequency, the same wavelengths, and so on. Let's talk about something called Poynting vector. What is Poynting vector? In fact, it is this thing, yeah, this is S, and you definitely know this is electric field, magnetic field. As you can see, this sign of X, this is not X, it's cross product, which means definitely this thing, E and B have to be perpendicular to each other, which is 90 degrees. And this is just permittivity of the free space. Okay, what is the meaning of Poynting vector? So basically, it's not a mistake, it's not I, it's Y, it's correct, because it's a name of a person, it's not pointing, like showing the direction, yeah? But it's really convenient to remember. So what is the meaning of Poynting vector? It is direction of energy flow. So as we have said before, yeah, here, in both situations, light has no any mass, but still it has an energy and momentum. And also it has an energy spread, as we have told you, in this case, this water molecule, this particle, might not travel itself here. However, it can spread its energy to its neighbors, so the energy of this particular molecule might transfer right here, and it works pretty well. Yeah, the same thing goes here. So as we have told you before, wave is something when we can transfer energy without transferring the thing itself. The same thing happens. So electric and magnetic fields, they just exist. They're not traveling somewhere. They're not teleporting somewhere. They're not moving. They're just oscillating. They are spreading energy, but not themselves. The same thing happens in here. So light spreads its energy, but not itself, yeah, in the nature of light. When we talk about this thing, direction of the energy flow, as you can see it, yeah, magnetic field goes up and electric field goes to right. Those are 90 degrees between each other, and this is the direction of the Poynting vector. As you can see, this thing is where our energy is going. Okay, I hope that you understood pretty well the wave nature of light, and basically we have several experiments which prove that. For example, Young's double slit experiment, which is something like this. Yeah, he has something like this, and it's just a plastic plate, yeah, let's call it like this. And in that plastic plate, in fact, he has something like this. Yeah, there is a narrow slits. Yeah, there are two of them, two narrow slits. Yeah, two holes. Let's say it's something like this. And he passes some beam of light, yeah, like a laser, let's say. But instead, we don't need a laser. In fact, we can use any straight beam of light, and while light is passing through this thing, it gives such kind of pattern. Yeah, it leaves this kind of image, which is pretty strange, in fact, because if it was just a straight beam of light, if it was just a ray, in fact, it must be just like this. But in fact, instead, we have something like this, which is the phenomenon which we call interference, which is this one. Yeah, but first, let's talk about diffraction. Diffraction is a phenomenon when we have this kind of waves approaching the slit, one of the slits, and while it hits some obstacle, it goes round. And when it goes round, this is something what we call diffraction. Yeah, it's when approaching straight waves while hitting the obstacle create wavelets. Yeah. And what about interference? In fact, it's something very similar to that. And as you can see, there are two holes like this one, and those two also create their own diffractions like this. And here we have the very same thing. But as you can see, these points are now intersecting with each other, which means that we will have some image right here, we will have some image here, and so on, where those starts to intersect. And that is exactly what we have in our image. We have some high intensity at certain points like this one, and low intensities like in this point. This is a dark fringe, what we call. Yeah, but right now we don't have to delve into that. Also, let's talk about polarization a little bit. We have some light. Yeah, later on we'll understand that light is approaching us in all directions, in fact. And when polarization happens, this wave of light passes just in one direction, and this would not be possible if light was something else than wave. Okay, I hope that you understood the wave nature of light pretty well. Right now, let's talk about the particle nature of light, which is this one. So, Einstein has won a Nobel Prize for his theory called Einstein's photoelectric effect. And its formula of this photoelectric effect, which is that photon is a particle approaching with some certain energy. This energy is calculated by this formula, which is hc divided by lambda, or we call it hf. Yeah, h is a Planck's constant and f is frequency of light. Yeah, and Einstein says that it's a photon particle. Yeah, we know what is a particle. Electron is a particle, proton is a particle, proton is +1, electron is -1. Neutron, which is just zero charge, it is also a particle, and so many other particles existing there. Yeah, and not all of them are fundamental particles. There are even quarks inside of protons and neutrons, but basically protons and neutrons and other stuff are also still particles, maybe even not fundamental ones. What about light? Light is a photon. Okay, and this particle has no rest mass, but still has energy and momentum, which means that while not moving, photon does not have any mass. Its mass equals to 0. But what does it mean? Like rest mass does mean that light might have some mass while moving. Well, maybe, just maybe. Some people say that we have this formula of Einstein E equals mc squared, and if you just change positions of the values in the formula, it will be mass equals energy divided by c squared, and that's how we gain mass. But the thing is, right now we don't apply that formula because mostly it is written in the old textbooks. Right now we try to avoid that idea. Okay. So what is the idea behind Einstein's photoelectric effect? So you have a metal bar. It basically works on metals, yeah, not gases or something else, on metals. And you have a source of light, a very strong source of light, for example, like our sun. And as you can see, it spreads some photons, yeah, and these photons travel in different directions, and ray idea of light comes exactly from this idea from Isaac Newton, who supposed that it might consist of some particles moving in straight direction. Okay, and what is the idea of Einstein? Is that photons coming to that metal, and it starts to interact with it in atomic level. So if we say that metal is, for example, it's iron, which is ferrum, and this ferrum has some protons inside, some neutrons inside, and also it has different sorts of orbitals, which is not the best idea. We have also Schrödinger's equation, which says that electrons, we don't have any kind of energy. Well, it's not something like orbitals. Instead, it's electron cloud. Electrons do not orbit the core, the nuclei. Instead, it exists everywhere at the same time, and they just hoop, yeah? Okay, but still, let's use this idea because it's pretty intuitive to explain, and let's say these green dots are each electrons, yeah? And we know that by chemistry, yeah, that we have this formula, which is 2n squared. It tells us that in each energy level, there might be just a certain number of electrons. For example, in the first energy level, we can have only 2 electrons, because by 2n squared, if we put here the first energy level, then it would be just 2, yeah? And we can have in any atom just 2 electrons, and if we continue by that formula 2n squared, it would be just 2 multiplied in second, it would be squared, and this thing will be just 2 multiplied 4, which is 8. And as you can see, it will be just 8 electrons in the second energy level, and so on and so on and so on. But what is the idea of Einstein? It's a photon which is coming here and hitting one of the electrons, yeah? And this electron is ejected after interaction with photon. Ejected means it is being hit out, yeah? It goes out totally. It does not just travel to the second energy level or third energy level. It just is ejected out totally, and it gains some kinetic energy, basically, because it has to move. And we know that kinetic energy is the energy of motion, exactly. And of course, we can open this energy of photon by Max Planck's constant and the speed of light, and also the wavelengths of that light, yeah, because we might have different sorts of light. Visible light is between 380 nanometers to 760 nanometers, but we also have radio waves, some ultraviolet, infrared, and so on, right? Okay, pretty good. And this thing is work function, which means that how strong each electron is bound to these energy levels. Well, this thing is this work function, okay? And if our energy of the photon would be enough, if it gets high enough and it's higher than our work function, it ejects electron out and it gains some kinetic energy to move out. Okay, good. But the main idea of today's topic is about ray optics. And as we have told you in the beginning, it's just a mathematical abstraction. What is happening exactly? In the macro scale, yeah, in everything what we can see with our bare eyes, light travels in straight lines. It does not travel like a wave. It travels in waves, as I have told you before, in 380 nanometers to 760 nanometers, which is the wavelengths of light. And in fact, it is something very small, because nanometer means something 10 to the power of minus 9. It's something very, very small, yeah? Okay, but in the macro scale, what we can see by our eyes, yeah? Light travels in straight lines, and it has some laws, for example, like reflection or refraction law. Also, there is something called dispersion, which we are going to cover in the next videos, yeah, of course. And at the beginning, yeah, let's say for reflection law, we have something like this. You have some kind of mirror, as you can see it right here, and you have some source of light which is giving light out, and this light coming in goes some angle, and if we draw some normal above that point where it hit the mirror, then we can see that those two angles, the angle of incidence, yeah, the angle of approaching light, and the angle of reflection, angle of light going out, they are equal to each other. Yeah, angle of incidence equals to angle of reflection, which is basically written like this: I of theta of I is equal to theta of R. Yeah, pretty good. Yeah, and let's talk about the refraction law. Refraction means basically bending light. Yeah, for example, we say that this is air. This part is air, and air has some density. Also, this part is water, and water also has its density. And when light comes from, yeah, for example, let's say here we have some sort of a source of light, and when light enters some medium, and it comes from less dense medium to high density medium, yeah, or even if it's opposite, it starts to bend. For example, this light comes with a certain angle, like alpha, yeah, we can call it anything. It starts to bend inside, and it will be some different angle, which is beta. This angle will be mostly smaller, of course, but it also matters if it goes from less dense to higher density medium, or from higher density medium to less dense medium. Okay, and it is described by Snell's law, which we are going to cover in the next video. Okay. And as you can see, yeah, of course, N1 and N2, these are called indexes of refraction, yeah, because air has its own density, as we have said, and water has its own density, as we have said as well, and they refract, index of refraction, yeah, I'm sorry, and they refract light differently. And this alpha and this beta are those angles that we have told you about. Okay, good. What about dispersion? It's something like white light going in, yeah. White light, in fact, is not something. It's not something different from other colors. In fact, it's a mix of all colors together. It has each color inside it. And when it interacts with some glass, for example, like this triangular glass, then each of the colors interact with this glass differently. And each of those colors starts to spread out in different angles. And we can see that phenomenon in our daily life, where we have the rainbow at the sky at rainy day. Yeah, and those colors give pretty much the same pattern, because they have the very important law. Each of these lights go just this order, which is this one is red, this is orange, yellow, green, blue, indigo, and violet. Yeah, this is the rule that they go, because red has the highest wavelengths, and violet has the lowest wavelengths, and so on. Okay, and the last thing that we are going to talk about right now is our lenses and mirrors. So these are called optical devices, optical elements, yeah, we call it, and we might have just regular lenses, but we can also have two types of spherical lenses. Spherical lenses are something like this. One of them, as you can see, these things remind us about spheres, yeah? If I continued to draw it, it would be just two parts of two different spheres, and the same thing goes for this one. That's why we call it spherical lenses, I'm sorry. And when we pass light here, they start to refract it at a certain angles, dependent on their characteristics, dependent on their focal point or their curvature. And the same thing goes for converging lens. As you can see, the difference between diverging lens and converging lens is that diverging, it spreads out, and converging lens, it collects inside, okay? And what about mirrors? Basically, we have also two types of mirrors, the concave mirrors, the convex mirrors. Basically, it's not that hard to remember them and differentiate, because concave, as you can see, cave is like this one. It's the entrance to the cave, yeah? And the second one, you just can remember by it's just different from this one, and so on. And mirrors, they differ from lenses just by one factor. Lenses, they refract, yeah, they let light in, but they start to bend it. And when we talk about mirrors, they start to reflect it. They just reject light and they pass them back. But these are also called spherical mirrors right now. As you can see, we can continue this thing, we can continue it here and so on, and this will be just spherical. In concave mirror, as you can see, they are collected inside, they are reflected back, but they are collected at a certain point. When we talk about convex mirrors, it's totally opposite. Light goes in, but they are reflected outwards and they cannot just collect. That's why there is also something called images, real images, virtual images, which we're going to talk about in the next videos. But for today, I would say that this is pretty much enough. I hope that it was pretty intuitive to you. I hope that it was understandable. But if you have any issues in comprehension of this topic, the nature of light, then of course you can write me privately and ask for your questions. Yeah. Okay, thanks for your attention. Goodbye.